Lecture 8, Cache Coherency. So to close out our topic on the subject of hardware, we're going to talk about cache coherency, which is looking at support in the architecture for memory ordering. And in particular, what we're looking at is a scenario something like this. Client in this case is a CPU. Each client has its own cache, and they have a common shared memory resource, and the little arrow between the two caches in the diagram is really the thing that we're focusing on today, and that is coordination is needed to make sure that everything works the way it's supposed to work. Because each CPU has its own cache, then if the same value appears in two caches, it could have two different values, and that would not be okay. The simplest possible solution to that is to say, well, if anything is shared, then it cannot be cached, in which case that would be horrible because, well, the compiler and operating system, everything would require the data to be read from main memory every single time. And as we've seen recently, that's actually awful for performance, and we don't want that. We want things to be in the cache, we want there to be less bus traffic, and we want there to be better performance. So instead, what we're interested in is coherency. And coherency means that the values in all caches are consistent. That is, nobody has some out-of-date value. That is, nobody is unaware of what the correct value is and ends up with somehow the wrong answer. And also that it's a system in which all CPUs have this shared memory illusion maintained. The system behaves as if all CPUs are sharing all of memory. Obviously, that's not true because different CPUs have their own cache, but the perspective of the CPU is that, yep, everybody is sharing it. Now, we talk in this lecture about CPUs as the clients, but as the diagram kind of indicates, this really could apply to other things as well. If you were writing a system that has, say, multiple processes and each has their own cache, then getting them to agree and see all the same data is valuable. I have recently been looking at a problem that has to do with caching whether or not a customer has unpaid invoices, and each node, each process could have that value in its own cache, but that's not very useful if you have multiple nodes, any one of which could end up responding to a request. And what you would actually want is for the different instances of that application to agree. So same thing, just substitute CPU in that case for a process. For now, however, we'll talk about CPUs because there's a lot to go on there. And we're looking at this from the point of view of a user, not an implementer, because ultimately we don't really get that choice. We get whatever hardware the system has. Okay, so here's a simple example that gives us an idea of what might be wrong. Initially in main memory, x is equal to 7, so CPU reads x. That results in the value of x being in its cache. I mean, not just x alone, but the page that x is in. And CPU 3 reads x and puts the value in its cache. CPU modifies x, setting x equal to 42. And CPU reads x possibly from its cache. Does it get the out-of-date value? CPU 2 reads x. Which value does it get? Again, it's kind of out of date. Unless we do something, CPU 1 is going to read invalid data, and we won't get the correct answers that we are looking for. I mean, in modern CPUs with 3 or 4 levels of cache, we frequently find that level 3 cache isn't very much faster than going to main memory, but this is the level where cache coherency takes place. And this makes the cache shared between different CPUs. So we are going to take advantage of that. For those who are curious, level 4 cache is used for sharing data with the integrated graphics hardware on CPUs that have that feature, but we're not going to go into that. And for the most part, we're imagining caches are not shared, and that's usually the case for level 1 and level 2 caches in your typical modern CPU. Okay. So, planes and trains. There are two strategies for how we could address the situation we just saw on the previous slide, where we might have some CPU getting invalid data. Okay. outside of a computing context, you could think about you and several coworkers. You have some shared information, such as there's a meeting in a specific room during a non-pandemic time, in a shared online calendar. Say the room has a little calendar, and you or anyone else could make changes to the event, and mind reading does not work. So the only way another invitee can know that something has changed is if they check to see something has changed, or if they are notified that a change has occurred. Usually we expect there's some sort of notification process where you get told, okay, the time of the meeting has been changed from 9:30 to 10:30, and that happens. So here's a story. I was flying to Frankfurt and then taking a connecting train, and I flew on Air Canada and took the train with Deutsche Bahn, hence the images being shown on the screen. Okay, so here's what happened. I experienced both kinds of notifications in the same day. Air Canada sent me an email that said departure time on your flight has been revised to 2200, which was a 20-minute delay. And so they sent me a notification that says, here's what changed. Here you go. And then when I landed and I got my bags and everything and I was waiting to take the train, Deutsche Bahn sent me an email that said, something on your trip has changed. Please check and see what it is using our app. It was my train being canceled. It's fine. There was another one less than an hour later. But still, that demonstrates the two kinds of notification. One is we're telling you what the updated value is. That is the new departure time for your flight. Or another one that says, listen, there's something that's changed, but you should look it up if you want. And it being my train cancellation, I mean, I don't know why they couldn't have emailed me that. It's not like I was any less annoyed by finding out after taking a second step of opening the app. Regardless of which method is chosen, we're going to end up with one of those things. Either we will tell the caller, hey, here's the new thing, you are now up to date, or we will tell them what information you have is out of date, and it's your responsibility to go get it if you want it. We can't pick neither of those and expect the right answer. And so our simplest way of doing something here is Snoopy caches, as they are called. And unfortunately, no, it is not this kind of Snoopy. Instead, it is the idea that caches are spying on one another. And they are therefore observing what happens with other caches. And so because all the CPUs are connected to a bus, the same one, each CPU can observe if a memory location is read or written by a different CPU. Okay, that sounds reasonable. This way, caches are kept up to date on what's happening, and they know whether or not they have to take any action. They don't rely on being notified explicitly. It is a little bit different from the analogy that I just gave about planes and trains, but that's okay. I don't consider it practical to observe every flight schedule change or every train schedule change as a person. Notifications are much better in that sense, since I'm not interested in every Air Canada flight on a given day. I'm interested in only the ones I'm planning to be on. Again, in a non-pandemic time when it is possible to fly, or at least advisable to fly. Okay, so this does require that every CPU has its own cache controller so that it can observe the bus and take action and what have you accordingly, but that's not terrible. That's an affordable cost. And so snooping is just reading the bus every time that you see something to see if any memory operation is relevant to us, and if it is, the controller takes appropriate action. All right, what does take appropriate action look like? Well, this is, we'll come back to. It's a distributed approach because there's no central state that's maintained, right? There isn't like one individual source of truth. where everything is recorded. Each cache with a copy of data from a chunk of physical memory knows whether it's shared or not. And when a CPU issues a memory write, other CPUs are watching to see if that memory location is in their cache. And if it is, then do something about it. If not, we don't care. It's irrelevant. The update on the flight to Vancouver is not relevant to me because I'm flying to Frankfurt. Great. I don't have any connecting flight that takes me to Vancouver. I didn't come from Vancouver. It's no big deal. We'll just ignore that. We will continue on. All right. If we do have something to do, then we take action. And action could be one of two things. It could be update or invalidate. Now, the Air Canada approach was update. They sent me the new value, and I know what the new value is, and I realize, okay, it's a 20-minute delay, which is honestly nothing noteworthy. But I've been informed. Here is the new update. Here's the information. I now have the latest information. The Deutsche Bahn action was invalidate. It said whatever information you had before about the train you were taking is no longer valid, hence invalidated, but it didn't tell me the new information. I just know that what I thought previously was the case is now no longer the case. And if I want to update myself about when is, or even what happened to that train, is it delayed? Is it canceled? It is my responsibility to go looking for that information. All I really know is that I need to check. So when I needed that information, I had to go get it myself from the source, their app. And really, either one of these approaches is fine. It is ensuring that I don't have out-of-date information. And you might have a preference on which one you think is better, but unfortunately it's not your decision because you didn't design the hardware in the computer that you're using, most likely. And as a person who wants to travel by plane or train, you don't get to choose what Air Canada or Deutsche Bahn's strategy is for updating you when there's a change in schedule. You just don't. It's not your decision. Write them a strongly worded letter, and I'm sure you'll get a nice letter back that says, thank you for your feedback, we have noted it, and we'll take no action. Okay, so let's think about, in the computer sense, the idea of how do we do such a thing as keeping everybody up to date. So the simplest type of cache coherence is what we call a write-through cache. That is, everything that is written to cache also propagates out to main memory. Therefore, all the cache writes also appear on the bus, the one that is shared between all of the CPUs, meaning that everybody can observe it. If another CPU snoops and sees it has the same location in its cache, it will either invalidate or update the data, and that is, again, based on whatever hardware we have. Okay. Does this work? Sure. When we are writing it out, we write to cache, and then it's the responsibility of the cache controller to put that on the bus, and anybody else who's interested will observe it. And for write-through caches, if you are writing to an invalidated location, you can bypass the cache and go directly to memory, which is called write no allocate. This kind of thing happens if you're just doing an assignment of x is assigned 42. It doesn't matter what the value of x was before, you're just overwriting it. You don't have to read it beforehand just so you can ignore that read and then overwrite it. You just straight up do your assignment. Okay. Now, our chosen approach and the kind of hardware that we have is invalidate. I unfortunately can't do a really good Dalek voice impression, but if I could, insert it here. Just use your imagination. And invalidation is honestly the most common protocol. It means the data in the cache of other CPUs is not updated. It's just noted as being out of date. And this happens, I think, because we're uncertain that the other CPUs are going to use that value anytime soon, so it's okay to just invalidate it because update takes a little bit more work. That is copying the new values to the CPU's cache, and if it was not going to use it anyway, we did some extra work for nothing, so there might be no benefit to doing so. Right. And if you want to do a read and there's a miss, then you can ask other CPUs to see who has the most recent cached version. This is a little bit like going into a room and yelling, does anybody have block, and then whatever block number of memory you're interested in some sort of multicast version of the card game Go Fish. But that works. The most recent value always appears in memory using the write-through cache strategy, so if nobody has it in cache or for some reason they don't feel like sharing, you can always go and fetch it from there. There are write broadcast protocols, so the opposite of invalidate as a solution, or at least the alternative to invalidate as a solution, in which case all caches get updated when there's a write to a shared block. But of course, that uses a lot of bandwidth. That is not necessarily a good idea because everybody is yelling about, well, I just changed this to that, and some people will be like, yeah, I'm noting it down, but I can't remember why I care. So that's not necessarily something that you want. It does prevent a cache miss that follows an invalidate, because when somebody has an invalid version, they have to go fetch the newest one. But it's not necessarily an overall win. And as we introduced in the beginning of this topic, since we're mere users and not hardware architects, we don't get to choose. We just have to live with whichever one is on the hardware that we get. Okay, so if we were thinking about implementing a write-through protocol, it looks something like this. Any chunk of memory can be in either the state valid or invalid. And events occur from the current processor, so this is our cache and our CPU, or they could be observed on the bus, in which case we will then figure out what to do based on that, and we can implement the following state machine. So if the data we have is valid in the cache and we read it, that's fine. There's no generated action. There's no step we need to take, and the next state is valid because nothing has changed. If it's valid in our cache and we do a write, it gets written out to the bus. That's what makes it the write-through protocol. And our next state is valid. We're the one who changed it. What we have in the cache is the most up-to-date version. If our state is valid and we observe a bus write in that location, then we know we should invalidate our data, and that means that we are just going to say, yeah, we no longer have the latest version, so its state is invalid. If the state is invalid and we do a write, then we are just overwriting whatever is there. It does generate a write on the bus, and it's valid in the next state because we just assigned x is 42. Therefore, we know we have the most up-to-date value, so no need for the invalid state there. We'll just go straight to valid. And if we have an invalid state and we do a read, it means we don't have the latest version, so we have to send the read over the bus to get the latest version, and the next state will be valid. Now, for simplicity, this isn't an architecture course, we'll assume that all cache reads and writes are atomic and apply this protocol to the example as before. So if initially in main memory x is 7, then CPU 1 reads x, puts its value in the cache, so it considers the state valid. CPU 3 reads x, puts its value in the cache, still valid. And CPU 3 modifies x is assigned 42, which is a write. This is going to write in the cache as well as send it out over the bus. CPU 1 observes that and marks the data as invalid. Then when CPU 1 wants to read x, it's from main memory, it's valid, and CPU 2 also reads x from main memory, and it also gets the valid version. So the change that CPU 3 makes in step 3 of assigning x is 42 will in fact be seen by CPUs 1 and 2, and everybody gets along and everything is happy. Now, what if in our example CPU 3 writes to x 3 times before it's read by anybody else? Then we would end up writing that out to the bus 3 times, and maybe that isn't as efficient as it could be. And one possible goal that we could have for improving our efficiency is to delay the write to memory as long as possible. If somebody needs it, we'll give it to them, but if they don't need it right now, then we don't have to tell them every single time. And you can imagine that the write-through protocol, if you are incrementing some value, hey guys, I changed x to 1, also I changed it to 2, I changed it to 3, and everybody else in the room is thinking like, no one cares, good for you, golf clap. Just in case anybody needs to know about x, I've now changed it to 4. It doesn't doesn't matter to anybody else, so they don't care all that much. So at a minimum, we have to add a dirty bit, which would be used to indicate that a particular chunk has not yet been written to main memory, and that would be sufficient. So what we're going to do is increase the number of states to 3. And the simplest type of write-back protocol, MSI, has 3 states: modified, shared, invalid. Invalid hasn't changed, but the other 2 are different. Modified, only this cache has a valid copy and main memory is out of date. So this means we've changed it, but it hasn't been published to the bus yet and hasn't been sent out to main memory. Shared, this location is unmodified, up to date with main memory, and it could also be in other caches, and those would also be up to date at the same time. So the initial state upon a first read is that the state is shared, and the implementation in the cache controller only writes data to main memory if another processor requests it. And that is if somebody tries to read X and we have it in the modified state, then we'll say, oh yeah, you should know the newest value is this. And during write-back, a processor can pick up the data from the bus if it needs. So it asked for the value of X. X is currently being published by a different CPU. We'll just grab it from the bus while it's on its way out to main memory and save ourselves a little bit of work. And so the number of states makes the state machine a little bit more complicated, but we'll manage. The bus write-back here is written as bus WB, and exclusive read on the bus is bus read X. So if our current state is modified and we do a read, there's no need to tell anybody, and we'll just stay in the modified state. And the same is true for a write. If it's modified, we're the only ones that have it, and we change it, no one cares, we won't tell anybody, so it remains in modified state. If it's modified and we observe a bus read, it means it's incumbent on us to put that information on the bus, so we do a bus write back, and it ends up being shared. If it's modified and we observe a bus read X, this is what happens if somebody tries to write to a value. Again, this is assigning X is 0 without reading it. That generates a bus read X, which says they want it exclusively, in which case we generate a write back and set our state to be invalid. If it's shared and we do a read, there's no change. It just stays shared. And if it's shared and we observe a bus read, then that's fine. We'll see that it is invalid. We'll see that it's shared. And if we see a bus read X, then it means invalidate. Somebody has changed it out from under us. Okay, that will work. If it's in a shared state and we do a write, it means we're assuming authority over this chunk of memory, so tell everybody it's ours and ours alone, so send the exclusive event on the bus, and the next state is modified. If it's invalid and we do a read, then we are going to read the data from the bus, and it goes into a shared state. And if it's invalid and we do a write, then it tells everybody else to invalidate what you've got, and we are taking it over. Okay, not too complicated. I mean, we added a little more difficulty to it, but it will be managed if every CPU does its job respectively when it sees the signals on the bus. And using the same example as before, we'll demonstrate that it works. So start again, initially in main memory X is 7, and CPU 1 reads X from memory, so we have a read and it goes into the shared state. CPU 3 reads X from memory, again, that's a bus read and it goes into the shared state. And CPU 3 modifies X by setting it to 42. So that generates a read exclusive event on the bus. So CPU 1 observes that and invalidates what it knows about X. And CPU 3 now considers the state of X to be modified. When CPU 1 wants to read X, that generates a bus read, and CPU 3 writes back the data and sets X to be shared. And CPU 1 picks up that value from the bus and also considers it shared. And when CPU 2 reads X from memory, that again generates a bus read and results in it being shared. Okay. So we can see that it works. It does get the job done, and we end up with all CPUs seeing the correct value in the end. And one of the most common protocols for cache coherence is a slight enhancement of the MSI protocol, MESI or MESI, and it adds another state. So shared and invalid don't change, but modified has been altered a bit, and we've added exclusive. So modified says only this cache has a valid copy and main memory is out of date. Exclusive says this cache has a valid copy, but it's consistent with that of main memory. And MESI allows a processor to modify data that's exclusive to it without having to communicate with the bus. And so this eliminates some unnecessary bus communication. If we are the only ones that have variable y in memory and we change it, it moves from shared to modified state under the MSI protocol. Then we tell everybody, hey guys, if you have y, invalidate it. No one cares because we're the only ones that have it. It would be unnecessary to tell everybody that. And so the MESI protocol allows us to skip that, save some work, reduce some bus usage. And you can imagine relatively easily, I think, some of the details about, well, the different state transitions, but the only one that's really sort of new and interesting is the idea that changing from shared to modified state doesn't result in something going out over the bus because we're going from exclusive to modified, whereas previously if we go from shared to modified, we have to announce it every time, even if no one cares. In the latest Intel i7 processors, there's the MESIF protocol. We had F, which is a forward state, which is the same as shared, except we have designated in advance who will respond to a request to transfer the data. So if CPUs 1, 2, and 4 all know about the value of X, and CPU 3 says, hey guys, I want to get in on this, can you tell me the value of X? Without this, there's an arbitration process for figuring out who gets the bus and who ends up sending the answer. The forward state designates which CPU is responsible for that in advance, allowing a bit more efficient usage of the bus because the different CPUs don't have to fight over who's going to be the one to give the answer. Whoever is the designated F of this data block will answer. Therefore, we get a bit more efficient use of the bus. We'll also close out our discussion by talking about false sharing. This covers the idea of cache coherence and loops us back into the software world and gets us a little bit further away from the hardware. But false sharing occurs when a program has two unrelated data elements that end up in the same cache line and same cache location. If you have two chunks of memory that are adjacent in their allocation, they probably end up in the same page of memory, and therefore they can end up in the same cache and cache line. So here are two character arrays of length 10, we'll call them A and B, and they are stack allocated in this example. They don't overlap, but they are located next to each other in memory. Now what we might observe here is that because they are next to each other, they'll probably end up in the same page and they'll probably end up in cache together. And therefore, if a thread writes to A and they are, again, in the same cache line as B, then B will also be invalidated and the CPU working on B will be forced to fetch the newest value from memory, even though there wasn't any overlap and B hasn't actually changed. That could be avoided by seeing to it that there is some separation between the two arrays. And one possible solution is heap allocating both of them, because it is unlikely that they will be exactly next to each other in memory, because heap allocation doesn't necessarily work like that. So that might work, it might not. Could we make both arrays bigger, which potentially wastes some space? Well, that's an idea. We could be sure that they don't overlap. Frequently, when we talk about how to organize your memory, I will be encouraging, we actually want to pack things more tightly together because then more items fit in the same cache block, and we have fewer cache misses and all those things. But sometimes actually the opposite is correct, and this might be one of those scenarios. So here is a false sharing execution time graph, where execution time is on the y-axis and byte separation here is on the x-axis. So in the diagram, byte separation of 11 in this means that the two arrays are adjacent. Anything less than that and they actually overlap, so that little hard corner in the graph at 11 is because below that, if you make A and B exactly the same location, then you get strange behavior. But execution time plummets very suddenly at about 50 bytes of separation. What's up with that? This is wasting some space, but at separation size 51, we are putting two arrays into two separate locations that do not have the false sharing problem. In which case, I think you would agree that wasting a little space is worth it. We wasted 50 bytes, nothing to write home about. It's not a huge, absurd amount of memory. However, it decreases the execution time of our sample program because we have a lot fewer invalidations of array B when the change was actually to array A, and vice versa. Another thing that's interesting is putting arrays in a struct and putting some padding can allow some future updates to the struct without breaking binary compatibility and those kinds of things, but we don't want to dwell on that too much. In any case, yeah, is wasting a little space worth it? Yeah. Is the false sharing problem real? Also, yes. All right, so to give sort of a quick summary, we saw the basics of cache coherence, and although we acknowledge it's more of an architecture thing, you can see how it might have an impact on your program, and knowing this allows us to make wise decisions. That is, we can think about things like, is there the potential for false sharing between these pieces of data, and if so, we can add a little bit of separation. We recognize that this is not a very complete understanding of cache coherence because that's a lot more hardware architecture than we want to talk about, but each of those approaches has its own trade-offs, as we got a little bit of a taste for in this topic. Sometimes the trade-off is there's just more hardware involved and therefore more complexity and perhaps more difficulty in manufacturing the chips. However, it is, for the most part, you get whatever protocol is provided to you by the hardware that you're using when you're working on it in your software. So that ends our short but hopefully interesting tour of hardware-type stuff and why it matters, and we will be returning to looking at the software components immediately following this.